In this video, we will discuss gravity, which is one of the four fundamental interactions, where the other ones are the electromagnetic, the weak, and the strong interaction, and they describe interactions between matter. Gravity was the first one to be described, and yet the only one not fundamentally understood. Maybe it doesn't even have a fundamental description. Maybe gravity is nothing but a feature of space-time itself, as in the theory of general relativity. No one knows, but it is considered a fundamental interaction for now, at least. Let's start by going into the issues of our understanding of gravity and compare it to the other fundamental interactions. Gravity plays an important role in our everyday life. Without this, we would be weightless and planets would fly out of orbit and the world as we know it would be impossible. In principle, living organisms can live with weightlessness, as in without gravity, as the astronauts at the International Space Station do, though it does seem to have an impact on health. The main issue is that gravity is what keeps our solar system together, and if gravity suddenly stops working, our Earth would just fly into empty space, and life would probably end quite quickly without the sun as an energy source. The other three interactions are essential for atomic structures and atomic processes, and their effects are more localized, especially the strong and weak interactions, which interaction range is less than the size of atoms. Gravity and electromagnetism both have an infinite range of interaction, but at the scale of our solar system, gravity is the dominant one. Likewise, the classical formulation of both gravitational and electrical forces have the same form, where k and g are constants, and m is a mass and q is a charge. But at a more fundamental level, gravity appears to be very different from the other ones. As mentioned before, gravity might have been the first fundamental interaction to be described due to its presence in our everyday life, but it's the only one without any fundamental description. This probably has to do with the fact that gravity is 10 to the 25 times weaker than the second weakest interaction, the weak interaction. That is 1 with 25 zeros after it, or in other words, the weak interaction is 10 trillion times stronger than gravity. Without going more into it, I can also quickly mention that the electromagnetic force is 10 to the 36 times stronger, and the strong interaction is 10 to the 38 times stronger than gravity. So the issue is that gravity is so much weaker that it doesn't have any significance or significant effect at the small fundamental level. The Standard Model neatly describes how the three other interactions interact with matter using force carriers or mediators in form of bosons. As an example, if two charged particles interact with each other, this is done by sending photons, or in layman terms light, between the two particles, and they can thus communicate in this way. At the current time, there has been no significant evidence to support a theory which would describe gravity in such a way. There has of course been proposed a so-called graviton boson, but such theories remain speculative for now, and the best theory for gravity is Einstein's theory of general relativity. Even though this theory has predicted many things which was later discovered, it also predicts things that probably do not exist, and it doesn't take into account quantum effects at small scale, so it's quite clear that general relativity is an approximation of a more fundamental theory. Thus, there's still more to learn about gravity. Since we're considering the framework of Newtonian physics, we will be discussing Newton's law of universal gravitation, where F is the attraction force between two objects with mass m1 and m2. The distance between them is r, and g is the gravitational constant. This formula works well to describe a system like the Earth orbiting the Sun. But we immediately see that if the object is massless, there is no gravitational force. This is clearly an issue, as gravity indeed bends light, and hence affects light, as we will see when discussing general relativity. Newton's law of gravitation was first tested in a lab more than 100 years after he published his theory. The idea is simple. All you need to do is to take two heavy objects with different masses and measure the distance between them, and then measure the force. The problem with gravity is again that it's very weak compared to the other fundamental interactions. This is in practice nice because otherwise you could hardly stand upright and you could just be pinned to the ground on Earth forever. But Henry Cavendish managed to make a sufficiently sensitive experiment using rather heavy objects by the 18th century standards, and as a result, he made the first lab evidence of Newton's law of gravitation and the first measurement of the gravitational constant, which today is measured to be around 6.67 to 10 to the minus 11th meters cubed per kilogram per second squared. Using his law of gravitation, Newton also became the first one to provide a correct description of tidal forces. Thus, using his law, one can obtain a pretty good approximation for the tides that we experience on Earth. The essential concept is that the solid part of the Earth, like the continents, stay more or less in the same place, while the oceans, which are liquid, can be influenced by the gravitational pull from the Moon. Thus, gravitational force from the Moon attracts the water and this creates tides. More specifically, the parts of Earth closest to the Moon and in the same place on the opposite side experience increased water levels, while in the places perpendicular to these two places experience a decrease in water levels. On the Earth, the biggest tidal factor is from the Moon, but the Sun also affects the tides in a similar way. Thus, when the Moon and the Sun both attract the water in the same direction, the really big tides occur. Let's just recap what we have discussed in this video. We have introduced the concept of fundamental interactions, which describe matter interaction, and discussed why gravity is like the odd kitten in the class and how it's quite different from the other interactions. Then we have looked at Newton's law of gravitation and considered some applications. In the next video, we will look at Kepler's laws, which can be derived from Newton's law of universal gravitation. This will give us the tools we need to quite accurately describe our solar system. As always, leave a comment with what you like, what you want to see in another video, and what can be improved. Likewise, if you enjoyed the video, please subscribe and like, and follow the channel. Stay tuned for the next video.